Hello and welcome to this new video. In this video, I'm going to solve the exercises of chapter 3. Let us start with the first exercise. We have to find the Laurent series of the function 2 over z squared minus 4z plus 3 on 3 different annuli. Okay, so we first start by decomposing f in simple fractions. Okay, so of course you have a method. You write f of z as a over z minus 1 plus b over z minus 3 because it's easy to factor the denominator. But here's a trick actually that can save you some computation. We write 2 as z minus 1 minus z minus 3, and now we get easily 1 over z minus 3 minus 1 over z minus 1. So a equal minus 1, b equal 1, if you like. Now, since modulus of z in the first annulus, modulus of z is less than 3, then z over 3 in modulus is less than 1. So we can expand 1 over z minus 3 after rearranging a little bit. So now, when we write 1 over z minus 3 as minus 1/3 over 1 minus z over 3, we have now a geometric series of ratio z over 3. And it converges because the modulus of the ratio is less than 1. Okay. So we can write the first term as the series, as a power series starting from 0 of minus 1 over 3n plus 1 zn. Okay. And now for the second, so this is makes for the first term. For the second term, minus 1 over z minus 1, we are outside the unit disk. So we factor by z. So we get minus 1 over z over 1 minus 1 over z. And now we have again a geometric series, but a geometric series with the ratio 1 over z. And this gives me a power series of negative powers. Okay, so I can write it as sigma n from 1 to infinity. So I just do a change of index, if you like, or change of variables. If you like, I can put n plus 1 equal k, then k would go from 1 to infinity of minus 1 over zk, right? But of course, the series does not depend on k. So I can put instead of kn or m or anything. And now, if instead of n I put minus m, so this would give me minus z minus n. So another change of index gives me a series of negative powers of z. So I can write it as, it's not really necessary to write it in this way. If you arrive at this series or this series, it's okay. So don't need to, but this just to illustrate the rotation. So if you write it in this way, it's perfectly acceptable. And now we just add the 2. Okay, so f is the sum of 2 series. The first series is a series of negative powers of z. And this is what we call the singular part. This is the singular part, plus a power series that we call the regular part of f. And this is true in the annulus of center 0 and smaller radius 1 and bigger radius 3. Okay, next annulus, we are outside the disk of center 0 and radius 3. So now 3 over z in modulus is less than 1. So we need to expand each term. So the first term, if we factor by z, we get 1 over z over 1 minus 3 over z. And then we expand this as a geometric series of ratio 3 over z. And that's it. So if I do a change of index twice, I can write 1 over z minus 3 as a series of negative powers of z. Now, and I can do the same thing for 1 over z minus 1, because now 1 over z in modulus, of course, is less than 1, right? Because modulus of z is bigger than 3, so it's necessarily bigger than 1. So this term also gives me a series of negative powers. So I just subtract them, and I get only this singular part. So there's no regular part in the Laurent series. And of course, this is true as long as modulus of z is bigger than 3. Now, for the last annulus, we have an annulus of center 1, right? And so it's a punctured disk, actually. It's a punctured disk of center 1 and radius 2. Okay, so z minus 1 over 2 in modulus is less than 1. So we have to expand in powers of z minus 1. So we take the first term and we rearrange it as 1 over z minus 1 minus 2. And if you multiply by minus 1, you get minus 1 over 2 minus z minus 1. And then we divide by 2, or we factor by 2, if you like. And we expand this in a geometric series of ratio z minus 1 over 2. And this gives me a regular part, actually. Now, the second term, I don't need to do anything because the 1 over z minus 1 is already a negative power of z minus 1, right? So minus 1 over z minus 1 is precisely the singular part. So the singular part consists of one term, right? So we see that 1 is a pole of order 1 and the residue is minus 1. And this is the regular part. So this concludes exercise 1. Exercise 2, we have to compute some residues. Let us start with sin z over z4. Now, in all these cases, actually, we have a pole. We don't have an essential singularity. Okay, so we have two methods, actually, usually, for computing. We have two options. Either we write the Laurent series of the function, or we use the formula given in the course. Okay, so, but it depends. Sometimes one is easier for computation than the other. Okay, so let us start with sin z over z4. This is the easiest thing to do, is to expand. Of course, we have to start by determining the singularities. Okay, here we have, in the first case, we have just one singularity, which is 0. So what we do, the easiest thing to do is to expand sign in a power series, and we have the radius of convergence plus infinity, of course, and then we divide by 4, by z4. So we get 1 over z cubed minus 1 over 6 over z plus z over 5 factorial. So the 6 is 3 factorial, minus etc. So we have, so the singular part is this, just consists of two terms, and this is the regular part. So we see that 0 is a pole of order 3, and the residue is the coefficient of 1 over z, so it's minus 1 over 6. This is the easiest thing to do. Now, if you want to apply the formula given in the course, we have to, the formula tells you that this is 1 over 2 factorial times the second derivative of sin z over z4 times z cubed, okay, evaluated at z equals 0. Okay, so we have to evaluate this, but this is really cumbersome to do, actually. Okay, because if you want to compute this, you will have to do a limit, and then you will have to do Taylor expansions, okay, power series expansion. So it's not recommended here. You can do it, actually, but it's really cumbersome. If you do it, check that it will give you the same result. Okay, I did it, actually, and I checked that it's minus 1 over 6. So how to decide which method to use? Well, this comes with practice, actually. The more you do exercises, the better you will become at recognizing poles and the order of poles and so on. Okay, so this concludes part A. Part B, we have to factor the denominator, and this is easily done. And we see that we have two singularities, a singularity at 0 and a singularity at -5. Okay, now for the singularity 0, we can write f as z-3 over z plus 5 over z squared. So we can write f of z as g of z over z squared, where g is z-3 over z plus 5. And in a neighborhood of 0, z-3 over z plus 5 is, of course, holomorphic. And at 0, it's -3 over 5, so it does not vanish. So this is a proof that 0 is a pole of order 2. Okay? And the more you do exercises, the better you become in recognizing or in computing the poles, the order of the poles, without just by looking at the form of the function. Okay? So now here, actually, we have two options. So either we expand the Laurent series, or we use the formula. Okay? Now for -5, similarly, -5 is a simple pole, as you may check, because I can write it as z-3 over z squared over z plus 5. So holomorphic over z plus 5. Okay. Holomorphic near -5, of course. So let us start by computing the residue at -5. So we just multiply the function by z plus 5, so we have a cancellation. And we just have to evaluate z-3 over z squared at z equal -5. Or just the limit of at z, it's the same thing, actually. Okay? Because this function is holomorphic now, so we can just evaluate it at -5, and this gives me -8 over 25. Okay? This is the formula from the course. Now, for 0, so the other method actually is to compute the Laurent series of f near z equal -5. But here in this case, it's lengthier. Okay, you can try it actually. Okay, so but you have to write z squared as z minus 5, z plus 5 minus 5, and then expand it as the derivative of a geometric series. It's doable actually, but it's not necessary here to do. So here the formula is easier, gives me the result in a quicker way. Okay. Now for the residue at 0, we just have, it's 1 over 1 factorial times the derivative of the function f of z times z squared. When I multiply by f by z squared, I cancel here, so I get just z minus 3 over z plus 5. And I have to evaluate the derivative at z equals 0, and this is very easy to do. The result is 8 over 25. And here again, we can expand f in a Laurent series, but it's lengthier. Okay, it's computationally more involved, so it's not recommended here. So when you deal with poles, you always have two alternatives. Now, which one is better? You have to decide from the form of the function and from your experience, actually. Question C. Here I will present both methods because they are equally. You have the same, so they're equally difficult actually. So first method, the formula from the course. So first we see that, so there's only one singularity, which is 2, and it's a pole of order 3 because we can write f as e minus zt over z minus 2 cubed, and this, if you call this g, then g of 2 is not 0. So it's a ratio of a holomorphic function over a third power of z minus 2. So we can just apply the formula, which is 1/2 1 over 2 factorial times the second derivative of what? Of z minus 2 cubed times f of z, which is just g. And this is very easy to do because you just differentiate this twice, you get t squared minus t times minus t, and this will give you 1/2 t squared a minus 2t. Okay, so this is very quick. Now the second method is not terribly difficult here because we can expand G as a power series, okay, centered at 2, not at 0. So this is why we have to add, subtract and add 2, and write G or e minus zt as e minus 2t times e minus tz minus 2. And now this is the exponential. As you know, this is 1, so e to the u is 1 plus u squared over 2 plus so on. So it's very easy to do the power series, to write the power series expansion of the exponential. And now we just divide by z minus 2 to the cube. So the first term will give me e minus 2t over z minus 2 cube. So we see that it's really a pole of order 3. The second term is e minus 2t times minus t over z minus 2 squared. And the third term actually is e minus 2t times t squared over 2 divided by z minus 2. And this is the residue again, by definition. By definition, the residue is the coefficient of 1 over z minus 2 plus higher order terms. So we see again that the residue is 1/2 t squared e minus 2t. So here in this case, both methods are equivalent actually. So you choose the one you like. But as we saw, it's not always the case that they are equally difficult. Sometimes one method is much easier than the second. Okay. And last point, z over z squared plus 1 squared. So we start by factoring the denominator. And we see that we have two singularities, I and minus I. And I hope you see that they are poles of order 2. Okay? You understand why. So the easiest thing to do is to apply the formula of the course, 1 over 1 factorial times the derivative of z minus I squared times f of z. So I eliminate this. And when I do the differentiation, I get minus z plus I over z plus I cubed. But it happens that it's 0. Okay. And a similar computation gives me the residue at minus I, and it's coincidence, it's 0 actually. And of course, the second method is not recommended here because it's lengthier. Okay, but you can try it if you like, just to double check the answers. Okay, so you have to expand, for example, in powers of z minus I. So you have to expand 1 over z plus I squared. So you write z plus I as z minus I plus 2i, and then factor by 2i, and then you get not the geometric series, but the derivative of the geometric series. Okay, and I think we did something in class like that. Okay, so it's lengthier, so it's not recommended here. Okay, so this concludes exercise 2. Third exercise, we have to compute an integral. So the integral of 1 over z cubed z plus 4. First, over the circle of center 0 and radius 2, positively oriented. And next, in the circle of center minus 2 and radius 3, positively oriented as well. So here, since we have two singularities, now, of course, in the case of the first part, so there are two singularities of f actually, minus 4 and 0. Okay, and usually only the singularities inside actually are relevant to the computation of the integral, because the singularities outside have index 0, so they don't matter here. Now, in the first case, so if we want to use the residue theorem, we have two options. Okay, first option or first way, but they are equivalent actually, but we have to justify So we have to give the conditions of the residue theorem. Okay. So we have Z0 is a pole of order 3, as you may check, and -4 is a simple pole. Okay, so we can take omega to be the entire complex plane. And then, of course, this is the ideal case. When we have a convex domain, then it's, of course, simply connected. Every loop is homotopic to a point. It's not a big deal. And F is holomorphic on omega without 0 and -4. And C is a loop in omega. The index of C with respect to 0 is 1 because 0 is inside the circle and -4 is outside, so the index is 0. Okay, so we can apply the residue theorem and we get the integral of f of z, if you call this f, it's 2 pi I times the index times the residue plus the index times the residue. Now, since this is 0, I don't need to compute this any, okay? So I just get 2 pi I times the residue. So in order to compute the integral, I just need to compute this residue. Okay, and I have a formula for this. So this is the first way for justifying, because we have to justify, we have to be rigorous. We have to justify the use of the residue theorem. Why can we apply it? Okay. I don't think I did something similar in class, okay, but this is one way of doing things. The second way is actually, we did something similar in class. We divide the circle from the other singularity by a line here, so just draw a figure, because we have two singularities, one at 0, 1 and -4, so I can divide them by a vertical plane. Okay, with equation. So, okay, so this is actually the right half plane. Okay, with the vertical axis at -3. Okay, and of course now this is convex. F is holomorphic on omega without 0. We don't care now about -4 because -4 is outside omega. And C is a loop in omega. The index is 1. Therefore, we can apply the residue theorem and we get the same result. Okay, so you see that the two ways are equivalent. Okay, in the case of the residue, I would prefer the first one, although I didn't explain in this way in class, but it seems that you don't need to worry about dividing into, right? So in practice, you can always take for the omega equals C, okay? So we get the same result. So we need to compute the residue, and for this we have the formula. It's 1 over 2 factorial times the second derivative of z cubed times f, which is just 1 over z plus 4, and if you compute that, you'll get 1 over 64. Okay, now when we have only one singularity inside a loop, a simple loop, we can also use Cauchy's integral formula, actually. And if you use the Cauchy's integral formula, you get precisely the same result. But if you want to justify the use of Cauchy's integral formula, you have to take omega like this, because you just have to have one singularity inside. Okay? So the integral is pi I over 32 because you have to multiply by 2 pi I. Now, second case is more interesting. Now we take omega equals C. We don't have a choice anymore here because this includes all the singularities. So we take omega equals C and we reason as above. Okay, so C is convex, etc. And so we have this. This is the we can apply the residue theorem and you get this formula. And as before, this is 1 and this is 1 because now C, it's not the same C as before. It's the circle of center -2 and radius 3. So both singularities are inside. 0 and -4 are inside the circle now. So they are 1. This is 1, this is 1. I denoted them in the same way, but okay, it's not the same circle as before. Okay, and now we already computed the residue at 0, but it happens that the residue at -4 is the same thing because it's just we multiply by z plus 4 times f, so we get 1 over z cube, and we evaluate this at z equal 4, or just the limit, same thing. Okay, so I get 1 over 64 plus 1 over 64, and I get, so at the when I multiply by 2 pi, I get pi I over 16, okay, because it's 2 over 32. Okay, so this concludes exercise 3. Exercise 4, we explained the method in class, and we did an example. So there's a method here. When we want to compute trigonometric integrals from 0 to 2 pi, we do a change of variables. So we put z equal EIT so that we replace the sign by 1 over 2i z minus 1 over z, which is z squared minus 1 over 2iz. And we replace the cosine by 1/2 z plus 1 over z. These are the Euler formulas, which is z squared plus 1 over 2z. Okay, and we have to also divide by iz. Okay, don't forget this term, because when we replace z by EIT, you have to multiply by the derivative of EIT, which is IEIT, so you have the cancellation here. So this is the function that I need to integrate over the unit circle, okay? Now, what we do is just simplify, so we reduce to the same denominator. When you reduce to the same denominator, you get here 2iaz plus z squared minus 1 plus z squared plus 1 times I, okay? And then you multiply by iz. So when you do the simplification, you'll get certain coefficients actually, but if you use the fact that 2i over 1 plus I is 1 plus I, and you get, because you will get these numbers, but they can be simplified. So when you do the simplification, you should get this function, 1 minus I over a second order polynomial. Now please check this and tell me if there's an error. I double checked, but anyway. So you should get this function. We have to integrate. So now we know that the integral over the unit circle of f of z is precisely this integral. Now, how do I compute the integral? I can, of course, use Cauchy's integral formula because, so, or the residue theorem. So they are equivalent in this case because if I factor if I look at the denominator, I can easily factor it, because how to factor this polynomial? I find the discriminant delta. The discriminant here is 1 plus I times a squared minus 4i, okay, b squared minus 4ac. Okay, and this turns to be a complex number, so I have to take the square root. Okay, before taking the square root, so if I simplify, I just use a trick here, because 1 plus I squared is just 2i, right? So 4i is 2 times 1 plus I squared. So I have already a squared here, 1 plus I squared times a squared minus 2. Okay, or if you like, 2i times a squared minus 2, same thing. Okay, but I put as a square because I just have to take the radical. So now there are two complex roots, minus b plus or minus radical delta over 2. Okay, and when I factor by 1 plus I get these two roots, 1 plus I over 2 times minus a plus radical a squared minus 2. And of course, this is something positive, because in my assumption, a should be bigger than radical 2. Otherwise, the integral is divergent, actually. Okay, you may have troubles in if a is less than or equal to radical 2. Okay, because sine t plus cosine t is, as you may check, is always bigger than minus radical 2. Okay. So we have these two roots. Okay. Now, only the roots inside. So these are the singularities of f, actually. Okay. Now, as we know, only the singularity inside the circle counts. So let us see which one is out inside, which one is outside. It's very easy. I just take the modulus. The modulus of 1 plus I, this is a real number, by the way. So the modulus of 1 plus I is radical 2. So the modulus of this constant is radical 2 over 2. And now this is a real number, but it happens to be negative here. Of course, I can have put minus 1 outside and get a minus radical. Then this would be something positive. Now, how to compute the absolute? This is just the absolute value actually here, because a is a real number. How to compute the absolute value of this? I multiply by the conjugate expression. So I get minus a squared minus the radical squared over minus a minus the radical. So in the numerator, I get plus 2. Okay, and this 2 cancel with this 2. And I can put the minus outside. Actually, I can, because this is something negative now. So this is a plus. So this is just radical 2 over a plus radical a2 minus 2. Now, the denominator is bigger than a, because this is a positive quantity. So the inverse is less than a. So modulus of z1 is less than square root of 2 over a, and this is by assumption less than 1. So z1 is inside the circle. Now z2 happens to be outside the circle, because if you compute the modulus as we did before, this is 2 over radical radical. So yeah, so we get, let's just check. So radical of 2 over 2 can be written as 1 over radical 2, and this quantity is positive and it's bigger than a. So modulus of z2 is bigger than a over radical 2, and this is bigger than 1. So z2 does not count. Okay, so we can apply the residue theorem by using the same justification. Of course, you can take here, if you like, the simplest thing to do is take omega equals c, and we just have two singularities, one inside, one outside. So the one outside does not count because the index is 0, and for the one inside, the index is 1. So we get, but don't forget the constant, which is 1 minus I. So it's 1 minus I over P of Z. And now it's very easy to compute the residue, because you just have to multiply by Z minus Z1 and replace by Z1. So I get 1 minus I times 2 pi I times 1 over Z1 minus Z2. And Z1 minus Z2 is very easy to compute. It's 1 plus I times radical A squared minus 2. Okay, because it follows from the formulas. And now 1 minus I times I over 1 plus I, actually, we already computed it, and it gives me actually 1. Okay. So the answer should be 2 pi over radical A squared plus 1. And the answer should be a real number. Otherwise, you know that there is an error. If you get a complex number, then this means that you have an error somewhere. So, but the formula is very simple. And we see here that what happens as a tends to radical 2, when a tends to radical 2, this goes to infinity. So this is a proof that the integral is divergent when a equals radical 2. Okay, because the denominator vanishes, okay, at some point. Okay, so this is the first integral. The second integral is totally similar. So if you follow the recipe that I gave you, you have to replace cosine by z squared plus 1 over 2z. And don't forget to divide by iz. When you do the computation, you should get this. And it's very easy to factor the denominator. It has two real roots, z1 and z2. So radical 2 minus 1 and radical 2 plus 1, because delta prime here, if you like, delta prime is 2 minus 1, so it's 1. Okay, so, and of course, only z1 is inside the circle. This is bigger than 1. So we can do the same justifications for the residue, because now Z1 is a pole of order 2 because I have a squared here. So I have to differentiate. And when you do the differentiation, you should get 4i z plus z2 over z minus, yeah. So I should have written here z instead of z, and then replace. When you replace z by z1, you should get minus I times radical 2. Okay. If you find any error, please don't panic. Just tell me, send me a remark so we can correct it. But in principle, I double check them. So but you check these computations actually, but because you have to train yourself to do correct computation. So in conclusion, the value of the integral is 2 radical 2 times pi. And I checked it with the computer actually. Okay, so same methodology. Okay, but here I was very sketchy because I don't want to repeat the same thing, but you should be able, in the exam, you should write the details. Okay. So this concludes exercise 4. Exercise 5, same idea. We have to evaluate. So here we have half of a circle, our familiar loop. So diameter followed by half a circle. And so we have to compute an integral of a holomorphic function, and then let r tend to infinity and deduce the value of a real integral, of an improper integral. Okay, so this is really standard. But we have to follow the indications. So first, we must find the singularities of f. The singularities of f are the roots of the denominator. And the denominator vanishes when z4 equal minus 1 or ei pi. So we know that, so we have to find the roots of minus 1, the root of order 4. So as you know from previous courses, the first root is ei pi over 4, which is just 1 plus I over radical 2. They are symmetric actually. And I think we did something similar in class and then in chapter 2. So we have 1 plus I over radical 2 and minus 1 plus I over radical 2. So this is just the symmetric with the rest of this one with respect to the y-axis. And then we have the symmetric of this one with respect to the x-axis. And so these forms actually the vertices of a square. And they all lie on the circle of on the unit circle because the modulus is 1. So you can picture them actually. Okay. So these are the roots, Z0, Z1, Z2, Z3. Now, since you are working on the upper half plane, only Z0 and Z1 are inside. Z2 and Z3 are outside, so they don't count. The index is 0. And here the index is 1. Okay? So now to justify, actually I wrote this before last year actually, so we can justify the use of the residue theorem. So I chose here one method, so just as we did in chapter 2, so we divide the roots Z2 and the singularity Z2 and Z3 from the loop by a straight line, as we did. Remember the red line in previous videos. Okay, or if you like, you can take omega equals c, and then you have to sum over all these things, but the index here is 0, the index here is 0, you just have the same thing. Okay, so this is the final result. Okay, so the integral is 2 pi I times the residue at z0 plus the residue at z1 of f. So you just have to compute the residue. Now here, the computation are not straightforward, so we have to do some tricks. And we did something similar in chapter 2 actually, because we had something similar we had z to the n here, if you like. So we know. I hope that you are convinced that all these singularities are simple poles. Okay. So we can apply the formula that I gave you in the lectures. So you have to multiply by z minus z0 and evaluate it at when z equals z0, or just find the limit because this is continuous. Now, here it's better to work with limits, right? And now I replace f by its value. It's e to the I alpha z divided by z4 plus 1. But the trick here is instead of writing z4 plus 1, I write it as z4 minus z0 to the 4. Because z0 to the 4 is minus 1, right? So now I have a kind of Newton's ratio, so z minus z0 over z4 minus z04. And so this is the limit of 1 over z4 minus z04 over z minus z0. So this is the limit of this ratio is the derivative of z4 evaluated at z0 by definition. And the derivative of z4 is 4z cubed, right? So, and I just replace the ei alpha z by z0, so it doesn't matter, right? So now, but this is the inverse here, so it's 1 over 4z0 cubed, okay? Why I'm doing that? Because I just want to find the simple formula for the residue. Now, I can, of course, compute 4z0 cubed by going back, but it's easier here to use another trick and multiply by z0, so that now we have 4z04, which is now minus 1. So this is minus 4 here. Okay. So this is e to the I alpha z0 times z0 divided by minus 4. Okay, and now I just replace z0 by its value. It's 1 plus I over radical 2. In the exponential, if you do this simplification, you get e to the minus alpha over radical 2 times e to the I alpha over radical 2. Okay, because you have I times, right? So when you do the simplification, you should get this result. And now we just multiply these two complex numbers. All right, so it's cosine. For the real part, we have cosine and minus sine, because I times I is minus 1, plus I times cosine times I, sine times 1. Okay, so this is the real part, this is the imaginary part, and this is, of course, is real. Okay, and if we do something similar for z1, actually we should have z1 here, not z0, it's a mistake. So we do the same tricks, and we get this result. So the same here factor, the same factor here, but now we have minus cosine plus sine, and the imaginary part is the same. So now I have to do the summation. When I add these two, I would have a simplification. Now the real part cancel, and they should cancel because I have to multiply then later by 2 pi I. Okay, so cosine minus sine cancel with this, and this, and in the imaginary part I get 2i times cosine plus sine, of course multiplied by this factor. So when I do the sums and multiply by 2 pi I, okay, so I get 2i over 4, it's 1 over 2, so 2i times 2 pi I, so the 4 cancel, and I get the pi outside, and then I get I squared, which is minus 1, cancel with the minus 1, so I should get something of this form, pi e minus alpha over radical 2 over radical 2 times cosine alpha over radical 2 plus sine alpha over radical 2. Okay. Now this is just to justify why the integral over the circle, the upper half circle, tends to 0. This is really standard, but I wrote it anyway. But in the exam you have to write these, okay? These estimates. Note that we are using here the second form of the triangle inequality. So modulus of z4 plus 1 is bigger or equal than modulus of z4 minus 1, not plus 1. Second form, right? And not 1 minus r4, because r is bigger than 1. So this should be something positive, okay? I see this error all the time. It's not 1 minus r4, it's r4 minus 1. So when I multiply by the length of this path, which is pi r, so I get that it tends to 0 as r tends to infinity. So now, on the other hand, we write the integral over this loop as the integral over the diameter. So here I can write t instead of x, not really a big deal, because here a parameterization is z equal x, of course, and plus the integral over this half of the circle. Okay, when r tends to infinity, this is constant, and we found it. This tends to the integral I'm searching for, and this tends to 0. So when r tends to infinity, I get this result. Okay, so this concludes exercise. Yeah, so if we want the integral from 0 to infinity, just divide by 2. Okay, now the last exercise. Okay, standard. So we take gamma r and CR as in the previous exercise, but now we have to take r bigger than 3 because it should contain the singularities of F, which are plus or minus 3i and plus or minus 2i. Now, I hope you see why 3i and minus 3i are simple poles, and 2i and minus 2i are poles of order 2. Okay, so we can justify the use of the residue theorem as before. I will not write it, but you write it. So if we apply the residue theorem, we should get this result. Okay. So only why? Because only 3i and 2r are inside. The other ones are just the symmetric, so they are outside. Okay. Now, if you want to compute to take the half circle in the lower half plane, then you have just to flip. You can do it if you like. So nothing prevents you from taking, instead of gamma r, the symmetric of gamma r. But then the orientation will be negative, and so pay attention to the orientation, actually. You can do it as, right? So we just have to compute the residue. The residue at 3i is very easy. Just multiply by z minus 3i. So we have a cancellation, and evaluate at z equals 3i. Or the limit, same thing. You should get 3i over 50. Now for 2i, because it's a pole of order 2, we have to take the derivative. Now here you have a little bit lengthy computation, but you can do it actually. When you compute the derivative of this and replace, but try to do simplification as much as you can. Okay, so because when you differentiate, you'll get factors in common. So please simplify before you compute. Okay, and when you replace z by 2i, you should get minus 13i over 200 or 13 over 200i. Depends how you compute. And okay, and now when you add these two, because now just if you want to reduce to the same denominator, you multiply here by 4, so I get 12i minus 13i. And then when you multiply by 2 pi I, so we have a cancellation, and the result is simply pi over 100. And now, as before, the integral tends to 0, but do the estimates. Okay, it's really standard here, and therefore we compute the improper integral, and the result must be real, otherwise there is an error. It must be real and positive, actually, because this is a positive function. Now, for the next one, b, we take f to be eiz over the same thing, so x replaced by z. And here we have to, so the singularities are the roots of z squared plus 1, which are I and minus I. This is easy. And the roots of z squared plus z plus 1 are standard, as you may know. Just compute delta, and you get minus 1 plus I radical 3 over 2. And this is called j, actually. And j is a root of unity. It's a root is a cubic root of 1. And j squared is also j bar, is minus 1 minus I radical 3 over 2. So these are the two roots. So they are related by very elegant formulas. So the roots are conjugate actually. Okay, and J. So yeah, so only I and J are inside the loop here. Okay. Note that modulus of J is 1 as well. So I and J are on the unit circle. So you do as usual, you justify the use of the residue theorem as you learn. And when you do that, you should get this formula. Okay, so now we have just to compute the residue of f at I and the residue of f at j. The residue of f at I is very simple. Just multiply by z minus I, so we cancel by z minus I, and then you replace that by I plus I to I squared plus I plus 1 is just I, because I squared plus 1 is 0. I times I is e to the minus 1, so I get 2I here. 2I times I, okay, so it's minus 2. So you should get minus 1 over 2e. Okay, now the residue at j is a little bit, you should be a little bit, we have to use some tricks if you want to get a simplification, okay? So same thing, multiply by z minus j, and evaluate this new ratio at z equal j. So you get eij over j squared plus 1 j minus j bar. Okay, so just have to compute this. If you compute, you should have, when you replace z by j, you should obtain radical 3 times radical 3 plus I over 2. And this is ei pi over 6. Because cosine pi over 6 is radical 3 over 2, and the sine is 1/2. So when you do your computations, you should get in the denominator radical 3 ei pi over 6. Okay. Now for eij, it's easier. Just go back to the formula for j. So I just have to multiply I by minus 1 plus I radical 3 over 2. And this would give you minus radical 3 minus I over 2. Now here we separate the real part and the imaginary part. So I get exponential of minus 3 over 2. This is radical 3. And what do I get? E minus I over 2 divided by ei pi over 6. So it's e minus I over 2 minus I pi over 6. So I can factor by minus I, and I get 1/2 plus pi over 6. Okay, there's no known formula for this. I don't know if you can find something, but we can leave it as it is, because it's not pi over 6. It's pi over 6 plus 1/2. And it's not pi over 2, it's 1/2 just. Okay, so. And now if you separate the real part and imaginary part, you get cosine 1/2 plus pi over 6 minus I sine 1/2 plus pi over 6. Okay? And now we have to add these two and multiply by 2 pi I. And this is not difficult. So we separate, so the real part, we have the exponential times cosine. Sorry, the real part we should multiply by I. So we get I times minus I. This is 1. So in the real part, I get the sine, because I times minus I is 1. And of course, multiplied by 2 pi and by this factor. Now for the imaginary part, I get 2 pi I times minus 1 over 2i plus this. So they are reversed. So in the imaginary part, I get the cosine plus this. And now we conclude as usual, the limit over the upper half circle is 0 by standard estimates. You do it. In the exam, you should write it. And finally, letting r tend to infinity and separating the real part and imaginary part, I get this result. Okay, so this concludes the exercises and the course. So congratulations, you finished the course. Please, if you find any error, don't panic, just let me know so that we'll correct it. In the exam, if you do some error, it's not the end of the world, because we look at the methodology actually more than and the reasoning, because anyone can do computation errors. Okay, but try to be precise. The course is not difficult, as you see by now. Just have to be precise and try to simplify your computations as much as you can. Okay, so thank you for your attention, and I hope we'll meet again.